All right, so today we have a fun one. We got aircraft flight instruments and navigational equipment. Now, this is probably one of the most daunting topics we have to go ahead and cover, especially as a private pilot. A lot of people get scared by this because it's just so much information, too much to know, and if you're not really mechanically savvy, it can be pretty confusing. But at the end of the day, we're just talking about six different instruments and two different systems. So we'll talk about, the Pitot-Static system, which consists of three instruments: our airspeed indicator, our altimeter, and our vertical speed indicator. And then we have Gyroscopic system, which consists of the attitude indicator, the heading indicator, and then the turn coordinator. So just six instruments. We'll also implement today a little bit of the Garmin G5 and how it actually gets that the information to go ahead and display all that good stuff on the primary flight display. And we'll go into some of the errors with these instruments as well, because that's really the main focus with this. If one of these was to fail, mid-flight, how are we going to make a safe decision to, one, understand what's going on, and two, indication where it doesn't put us in a dangerous scenario, really. So first one, we're going to go ahead and talk about the first system. We're talking about two systems. There's the first system here, Pitot-Static system. Pitot-Static system, like I said, is going to be the altimeter, airspeed indicator, and the vertical speed indicator. The Pitot-Static system is measuring two different pressures. So first pressure is going to be static pressure. This is going to be the ambient air around the aircraft that is undisturbed by the motion of us flying through it. Where's this ambient air or there's static pressure entering? Well, through a static port, as we can see over here. We have one, maybe two on some of the aircraft that we fly out here in the Phoenix area. You might have one or two on your aircraft, usually situated on the side of the fuselage. But static air goes ahead and enters through this port, and then it is basically ducted to the instrumentation. Then we have dynamic pressure, which is ram air. So ram air coming in through a pitot tube, as we can see here. Coming in through a pitot tube and then heading straight into the airspeed indicator. We also have to compensate for different changes in altitude. So we connect this to a static line as well. That's all dynamic pressure is. It's going to be this ram air minus the static air. So you can think of it, the ram air coming in through the pitot tube minus the actual air mass that we're actually flying through. Because, if we're flying at high altitudes all the time, pressure would always be really, really low. And these indications would always be really, really low. But we'll get more into that when we talk about the airspeed indicator here. So the airspeed indicator, already discussed, this is measuring dynamic pressure. This is all this thing is doing. It's just measuring a pressure differential. What it wants is dynamic pressure. So it wants that ram air coming in through the pitot tube, in through the pitot connection, and into the diaphragm. The diaphragm, we can kind of think of it like as a balloon or the human lungs. More air comes in through that pitot tube. These lungs want to go ahead and expand, or this diaphragm wants to go ahead and expand, giving us an indication on the airspeed indicator that our airspeed is rising. Say we slow down, less ram air coming through, less pressure being created, and that diaphragm is going to go ahead and contract, so we get a decrease in airspeed. So we know how we get the ram air here. Why is this also connected to a static line? Well, like I said before, if we were flying at high altitudes, this thing would always read super low, because the higher we go in altitude, the less dense the air is. Hence, the less dense ram air coming in through this pitot tube. So we have to connect it to that static line to go ahead and compensate for that. Like we said, this measures dynamic pressure, which is going to be that ram pressure minus the static air. And that's finally how we get it. That's all it's measuring here. So in review with that, it always gets a little bit wonky with explaining why it's connected to that static line. If it wasn't connected to that static line, it would always indicate lower airspeed at higher altitudes and higher airspeed at lower altitudes, because more dense air at lower altitudes. So we connect it to that static line to go ahead and compensate for that. Now, let's talk about the altimeter. The altimeter is going to give us our height above sea level if calibrated correctly. So if we set it to that local altimeter setting, and we listen to that ATIS for that day, yes, it'll give us correct indications. But if we go ahead and rotate this Colesman knob and we don't have the correct inches of mercury set for a given day, then it will give us incorrect indication. So it's kind of garbage in, garbage out. But yeah, we have the face of the instrument here. We have 20-foot tick marks along. We also have 100-foot tick marks as well, every 5 20-foot tick marks. Shorthand, you kind of read it like a clock. So in this scenario, we have 1, so that's indicating 1,000, and the big hand's on the 3, so we have 1,300. What's actually going on inside of this instrument? Well, this one's just connected to the static line. Like the airspeed indicator is connected to both the pitot tube and the static port. This one's just the static port. So we have the stack. It looks like a bunch of pancakes in here. They're sealed aneroid wafers. So as in contrast to the diaphragm itself, it's not sealed. It's constantly connected to a static line. In this scenario, when we rotate this Colesman knob, we are changing the reference level with these sealed aneroid wafers. Inside of these aneroid wafers is 2 inches of mercury. They calibrated it so it's standard pressure inside of those. But if we want to go ahead and calibrate it, say it's a non-standard day, we can rotate this Colesman knob here and change the size of these aneroid wafers to really get an idea of what our reference pressure is for a day. As the static air goes ahead and comes into the instrument casing via the static port, it has a chance to either squeeze these aneroid wafers or let them expand. So, let's give a scenario where we're starting a climb. As we start climbing, we start experiencing less and less pressure inside of the instrument casing. These aneroid wafers are going to get a chance to expand, showing us on the face of the instrument a gain in altitude. Say we start to descend, higher pressure inside of that instrument casing, it starts to squeeze these aneroid wafers. And that's when we start to get a decrease in our indication on the altimeter. The reference pressure in the diaphragm can be adjusted in the Colesman window. We always got to make sure we're doing that. That's the biggest thing with the altimeter here is, it's garbage in, garbage out. So, and a big one here is the errors associated with the altimeter as well. So we have 2 different types of errors. We have non-standard temperature and non-standard pressure. So from hot to cold, look out below. You'll hear that a lot. So on hotter, if we're going from an area of really high temperatures, the pressure levels for a given day are higher in the atmosphere than they usually would be. If we don't change the altimeter setting and we're going to an area of colder air, these pressure levels are going to be lower than actual. So that's because this is going to put us very dangerously close to the ground if we do not get an updated altimeter setting. So make sure we're doing that. And then we have the non-standard pressure. So high to low, look out below, low to high, look high in the sky. So say we left an airport of 2.9 on the altimeter setting here. We know it's higher pressure over here. Now we're going to an area of lower pressure. So the altimeter setting is 28.36. We kind of go on this slope just like with the non-standard temperature day if we don't change that altimeter setting. Because in both scenarios, the altimeter kind of translates the decrease in pressure as an increase in altitude, so it tells you to descend, and that's why we're kind of flying this slope all the way down. So be wary of those errors. Just understand we have to go ahead and get a new altimeter setting along our route. Then we have the last instrument in the Pitot-Static system. This one also just works off of the static system, just like the altimeter does. But this is going to give us a climb or a descent in feet per minute. So if we look at the face of the instrument here, we got some tick marks here. Those are all going to be hundreds of feet. Those tick marks, 500, go up to 1,000, goes all the way up to 2,000. That's actually one of the errors for this. If you go in excess of 2,000 feet per minute and a descent, it will not tell you any further than that. Yeah, as we climb, static pressure decreases. As we descend, static pressure increases. So let's look at the instrument here. So we have a Diaphragm, again, we have a diaphragm that's connected directly to that static port. So as the air pressure outside is changing, so is the air pressure inside of the diaphragm. Now we also have the instrument casing connected to the static port as well. So what's the difference here? If one's connected to the static port, so is the other. One, it always just reads 0 because it's no pressure differential going on. Well, the pressure inside of the instrument casing itself is let in and out via a calibrated leak. So it's a small orifice that allows the air in the instrument casing to change much slower than the air inside of the diaphragm. So let's just give a scenario here. Let's say we start to climb. We know that we experience lower pressure inside of that diaphragm instantaneously. What's going to go ahead and happen in the instrument casing? Well, it's not changing as fast because it can only change via that calibrated leak, so it's much slower. So as we start to ascend, we have lower pressure inside that diaphragm and higher pressure inside of the instrument casing. So it's going to go ahead and squeeze that diaphragm. Once it squeezes that diaphragm, we get an increase. It gives us an indication in feet per minute of a climb. Now let's go ahead and give a scenario where we descend. Say we start descending, we start experiencing higher pressure inside of that diaphragm. And then in the air in the instrument casing, yeah, it's getting higher, but not as fast as the air inside of the diaphragm, so it's going to be lower. So high pressure inside of the diaphragm, lower pressure in the instrument casing. That diaphragm is going to be allowed to expand. And when it starts to expand, we get an indication of a descent in feet per minute. Now there is a lag with this, about 6 to 9 seconds, so it's not instantaneous. So you actually have to be stabilized in a climb or a descent to really get an accurate indication of what your climb or descent really is. And yeah, when we're straight and level here, what's happening inside that diaphragm? It's not changing. It's equal to the static air around the aircraft. And then what's happening in the instrument casing? It's also not changing. So what's it going to read? 0. It's just going to stay the same. So yeah, that's going to be the vertical speed indicator. Now let's talk about some blocked pitot-static system situations. Let's go down here first. We'll go to a few different scenarios. So pitot ram air source and drain hole blocked. So it could be an icing scenario. It could be some sort of debris, maybe an insect got in there. If the pitot-static, if the pitot ram air opening here is blocked and the drain hole is there to go ahead and allow a moisture and debris to fall out, say that gets blocked as well. Now we have sealed air inside of this pitot tube. If we start a climb, it's going to want to go ahead and expanding that diaphragm, the airspeed indicator. So increases. Our airspeed is going to go ahead and increase with altitude gain and decrease with altitude loss. We know that the airspeed indicator is the only one connected to the pitot system as well. So if we only have a problem with the pitot tube, the altimeter and the vertical speed indicator is going to be unaffected. So nothing changes with them. Say the pitot tube just got blocked and that drain hole stayed open, it's just going to read 0. It's just going to drop to 0, and the altimeter and the VSI will remain unaffected. Static source blocked. So airspeed indicator is going to go ahead and show us a decrease in airspeed with altitude gain and an increase with altitude loss because we lost that static source. It's not compensating for changes in altitude anymore. It's always going to read lower at higher altitudes and higher at lower altitudes. The static system is blocked now. So we have basically just sealed air inside of the instrument casing, and it's not going to be changing. So the altimeter is going to go ahead and freeze, and then with the vertical speed indicator, it will not change. It will go ahead and read 0. Then we have both static and pitot sources blocked. All indications are going to go ahead and remain constant. Everything's going to freeze. So your airspeed indicator, your altimeter, and your VSI is going to go ahead and freeze. Let's jump up here with the Garmin G5. If you are lucky enough to fly with those, any sort of blockage or unreliable information that might be coming from a pitot-static system, it will display it on your Garmin G5 as a red X. So it'll actually cancel it out for you. With the steam gauge instruments, these errors are pretty tough to actually dissect and know what's going on mid-flight. Garmin G5 tells you they can't be trusted with that red X, but with old steam gauge instruments, you kind of got to figure that out yourself. And you can imagine how that could lead to some interesting scenarios, especially if you were in the clouds and you couldn't see outside and you were depending on that instrumentation with your life. So that's why this is a huge topic when you get a little bit closer to instrument training, but good base for a private pilot as well. Now, let's say that static source got blocked. Say, we got some sort of debris on that static port, and it's giving us unreliable information. What other static source do we have? Well, in the 172S at least, we have an alternate static source. This is going to be using air from inside of the cockpit to go ahead and feed the instrumentation. Before we go ahead and pull this knob to utilize the alternate static source, we need to do a few things. First thing we need to do is close all the windows and the vents inside of the cabin. And then next thing we can do is open up all the cabin heaters and the windshield defrost and the cabin air as well. Why do we want to do this? Because we have higher pressure outside and lower pressure air inside because of the Venturi effect. So air is being accelerated through the cabin, creating lower pressure inside, so we get incorrect readings on all of our instrumentation. Our airspeed indicator will read higher than actual. Our altimeter will read higher than actual as well. And our VSI, when we pull that out, it's going to show a momentary climb for a second and go ahead and drop. And that's just the Venturi effect. That's the rushing of air from outside, higher pressure through the cabin, lower pressure, just making everything read a little bit high. So that's going to be the alternate static source there. One thing that I didn't touch on is pitot heat as well. Say we had that pitot tube blockage. We know with the static source blockage, we can go ahead and use that alternate static source. What about the pitot tube? Well, we actually have an electric coil inside of the pitot tube itself. If we did get a blockage with, icing conditions, if we, got some sort of, mixed clear rime ice on the pitot tube itself, we can go ahead and turn on pitot heat to use that electric coil to burn off some of that ice. Two conditions we must meet. We must be in at least less than 10 degrees Celsius and visible moisture, because that's when icing is actually going to occur. So we have two options there. Static source gets blocked, use the alternate static, and then if we get a blockage with the pitot tube, use that pitot heat. All right, now we're off to gyroscopic systems. So gyroscopic system is going to be working off of three instruments here. We have the attitude indicator, we have the heading indicator, and we have the turn coordinator. A gyro is a small spinning wheel that is mounted so that it remains spinning in the axis in which it is spun. So if you were born, in the early 1900s, this might have been the only toy you had to play with. It was that small spinning top. You would pull a string through it. The faster you pulled the string, the gyro would spin on the table or whatever you put it on, and it was more rigid when you spun it fast. When you spun it really slow, it started to wobble around and do all sorts of crazy things. We do the same thing with aircraft. This is called rigidity in space, which is going to be one of the first principles of the gyroscopic system. Rigidity in space basically just says the gyro wants to go ahead and remain spinning in the axis in which it's spun. So it could be spun in the vertical or the horizontal axis. Vertical axis, it's standing up like it is in this first picture, or in the horizontal axis on its side. Now, the second principle we have is precession. So when a force is applied to this spinning gyro, it's actually experienced 90 degrees ahead of rotation. So if we took this gyro here and imagine, we spun it on a table, we were looking down on it. Say we touched it at the 12 o'clock position. Well, we're actually going to feel that gyro's going to experience that force at the 3 o'clock position. Say we touched it on the bottom of the gyro, and we're assuming it's spinning clockwise here. If we touch it at the 6 o'clock position, we'll actually experience that force at the 9 o'clock position. So two principles there. Rigidity in space wants to stay in the axis in which it's spun. Precession, if we touch it, we will experience a force 90 degrees ahead of rotation. And we use both of these principles with all three instruments to go ahead and give us orientation, essentially. So gyroscopic power system, before we talk about the actual instrument itself, how do we power up these gyros? How do we actually get them spinning? Well, I'll just zoom into this schematic from the pilot information manual, this black and white one down here. Now, some backstory about gyros. Gyros are designed with little etchings on the side of them. We call these rotor vanes. And they're built in a way so if air is pulled around the gyro, it creates friction and it actually spins the gyro for us. That's why we have a vacuum system. So we have two engine-driven vacuum pumps. This is specifically for the Cessna 172S. Your aircraft might be different. Look at your POH. Two engine-driven vacuum pumps that are pulling air through a air filter on the left side here. It has two routes. It can go through the attitude indicator or the heading indicator. Both have gyroscopes inside of them. We're pulling air through them because we want the air to create friction on the gyro. Those little pockets, those rotor vanes, spinning the gyro so we can go ahead and get some indications of orientation. After that, we have a vacuum relief valve. Say, that the vacuum pressure got too high, we can go ahead and dump some of this vacuum pressure via the vacuum relief valve. And then we have a manifold check valve right in the middle over here. That's basically if one of the engine-driven vacuum pumps fails, this will close and will reroute all of the vacuum pressure air into the good engine-driven vacuum pump. So we still have some good suction going on. So with the vacuum system itself, we also have this vacuum slash amp gauge here. Just basically our suction gauge. We will get a enunciation on the enunciator panel when this goes below 3 inches of mercury. The normal operating range for it is going to be, that green arc is going to be 4.5 to 5.5 inches of mercury. And how do we actually get these readings? Well, if you see just aft of the engine-driven vacuum pumps, we have these low vacuum switches, which are connected to our enunciator panel. So that's a vacuum system we go ahead and utilize in our aircraft. And as you can see, there's electric ones, Venturi tube, wet type. Don't have to worry about those. Just know we use the dry air vacuum pump for the attitude indicator and the heading indicator, and then we use the electrical system for the turn coordinator. So let's talk about the attitude indicator. This is going to be our first gyroscopic instrument. The attitude indicator is going to give us indications of pitch and bank. So we can see here, we zoom in on this top left one. Let's zoom in on the middle. We have the artificial horizon. We actually align this with the actual horizon on the ground. We have bank indications in the 10, 20, 30, 45, all the way to 90 range. And we also have pitch indications from 5, 10, 15, and 20. Your aircraft might be different. This is just the one depicted here. So it's giving us pitch and it's giving us bank. Well, how does it actually do this? So as you can see here, we have a gyro in the middle here, and it's spinning on the vertical axis. We are utilizing rigidity in space here. We want to move the aircraft around the gyro without putting a force on the gyro and precessing it. So it's mounted in a way where we have these gimbals that allow the aircraft to go ahead and rotate around the gyro without affecting it at all. So we still have this reference point. If we pitch nose down, the gyro stays. Pitch nose up, right bank, gyro stays. We're just moving around the gyro in reference to the artificial horizon that we set it to. That's all it is. Some errors with this, crazy banks, pitches, all that stuff can create precession and can cause this attitude indicator to go ahead and tumble for us. But most of these errors are pretty small. And once the vacuum system kind of catches up and spins that gyro again, it's a self-correcting system for the most part. Now we have the heading indicator. Now, this kind of looks like a compass. It's like, awesome, I can get magnetic readings from this thing. It just tells me everything, and it's so much easier to read than the actual magnetic compass. That's actually not how it works. We have to slave this, or go ahead and put the magnetic heading on the magnetic compass, from the magnetic compass onto our heading indicator. So we actually have to adjust it about 15 minutes because the Earth rotates about 15 degrees per hour. So this is not a north-seeking instrument. We actually just set what the magnetic compass says, and we put it on here. So if that, magnetic compass said heading was 300, we go ahead and take this knob down here, move it to 300 like they did in this example. That's really all it is. This gyro is mounted on the horizontal axis, so on its side here, and allows us to roll and yaw around it. When we roll and yaw around it, we actually change a gear. We see this compass car gear moves when we roll or yaw. When we do that, the face of the compass card itself will change with these headings. So just like the attitude indicator, it's going to go ahead and have some errors with it as well. So those 15 degrees per hour is going to be how fast that Earth is turning. So we have to go ahead and change this every 15 minutes or so, because this is not a north-seeking instrument. But yeah, that's going to be the heading indicator there. Then we have the turn and slip indicator. This is going to be the old version of the turn coordinator. We'll just talk about the turn coordinator today. This is going to be the only gyroscopic instrument that is powered off of electricity. So we spin this gyro via electricity in the horizontal axis here. Now it gives us two things, actually three things. When we start a turn, it's going to give us rate or roll, so the actual rate we're beginning a turn. When we are stabilized, it gives us rate of turn. What is rate of turn? Rate of turn is just the degrees per second the nose of the aircraft is actually turning. Standard rate is going to be 3 degrees per second, which, if you do the math, if you want to make a 180 degree turn, it'll be a timer for 1 minute. If we want to make a 360 degree turn, it'll be 2 minutes. What do we do if this thing fails? How do we actually get our turn rate? This is more of an instrument rating question. We would use our attitude indicator, but the angle of bank that we would need would be equal to our true airspeed divided by 10 plus 5. So that's kind of how that works out there. Now we also have, we have this miniature airplane with these tick marks that's indicating level flight at the moment. If we were to put this left wing on this left tick mark over here, that would be letting us know that we have a standard rate turn established. So about 3 degrees per second. Now we have this black ball inside of this tube here. This ball is actually filled in a tube with kerosene. And all this ball is doing is telling us if we're in a slip or a skid scenario. So it's balancing the centrifugal forces, so the forces to the going outside of the turn, to the centripetal forces, the force of gravity to the inside of the turn. So if we make a right turn here, and this ball shoots outward, we know that the centrifugal force is much greater than the centripetal force. So we're in a skidding turn, which is very dangerous at low altitudes. Say we go ahead and make this right turn and the ball moves to the inside of the turn, we know that the centripetal force is stronger than the centrifugal force, so we are in a slipping turn. How do we go ahead and counteract this? How do we make coordinated turns? We step on the ball, which would be very important. When we talk about stall and spin awareness, we want to be making sure that we're stepping on this ball and maintaining coordination through all that. So not only is this giving us rate of roll and rate of turn once stabilized, it is also giving us the quality of our turns. How does it do this? Well, it's mounted on its horizontal axis. Its framing is canted 30 degrees upwards. So if we yaw, this instrument actually precesses. So yaw is felt at the front or the back of the instrument. So if we're looking at it at the side here, at the 6 and the 9, at the 3 and the 9 o'clock positions, precession we know acts 90 degrees ahead of rotation. So it'll move this gyro to the left or right, turning this miniature airplane. Now, how does it actually get rate of roll? that's the difference between the turn and slip and the turn coordinator. Turn slip is a perfect 90 degrees across that gyro. Roll is measured at the top and the bottom of the gyro, so the 12 and the 6 o'clock positions. So if we try to roll, this gyro will experience a force, in this example, at the 12 o'clock position. We will actually experience this, because of precession, at the 6 o'clock position. Well, the way that this gyro is mounted, we can actually feel that force because the framing for the gyro is blocking it, if we can think of it like that. If we go down here, we can see how it's canted upwards. So we still feel that force at the 12 o'clock position, but now when we roll, we can actually see the force at that 3 o'clock position, because the framing is out of the way, because it's canted 30 degrees up. Without having an actual gyro, or using a laser point or anything like that, that is the best way I can describe to you why that thing is canted 30 degrees upward. It's just so we can get rate of roll. So yeah, in summary, turn coordinator gonna be electric, turning that gyro, mounted on that horizontal axis, canted 30 degrees upward, gives us three things: rate of roll when initiating the turn, rate of turn when stabilized, and quality of turn via that inclinometer. This is just more information on the inclinometer. We already touched on all that stuff. Slip or a skid, make sure we're stepping on the ball. Yeah. Now, we can wrap up with some Garmin G5 stuff. So how do we actually get the information from our gyroscopic system and our Pitot-Static system onto one primary flight display? Well, the Garmin G5 utilizes two sources. We have the air data computer, which is going to be up here. We have one in the top right, which has a actual pitot inlet and a static inlet. So it's actually connected to the Pitot-Static system. So whatever the Pitot-Static system senses, this air data computer senses. Hence, when we get any sort of blockage, we get that red X, because the air data computer is also getting a blockage, because it gets its information directly from that Pitot-Static system. So the air data computer will get its information for the airspeed, the altimeter, and the VSI, and it gives us all that information on the airspeed tapes, altimeter, and VSI tapes here. And if any of those goes out, we get a red X. So it's just a computer that's connected to our Pitot-Static system and displays it there for us. The AHRS, or the Attitude Heading Reference System, is a little bit more complicated, but this is where we get our attitude indicator, our heading indicator, and our turn coordinator. So it kind of just meshes all three of those into our primary flight display. It's going to use three different things to go ahead and give us our information. A accelerometer, which is basically our skid and tilt sensor. It basically uses microchips and different sensors inside of the microchip to actually feel accelerations across a measured mass. It's very complicated. Just know it uses an accelerometer, skid and tilt sensor essentially. Then it also has an MEM gyroscope, memory gyroscope. This is basically just a microchip gyroscope. Very complicated stuff. Just know this basically gives us our attitude. And then we have a magnetometer, which is basically a metal plate they flow electrons through. That's what's really cool about the Garmin G5, because we no longer have to slave it to a magnetic compass. This heading that we get up here is a magnetic heading because of that magnetometer. Now, how does it connect these two systems? How do we get these two dual G5s talking to each other? Well, a high-speed data bus link, which basically works as a Ethernet cable between the two, so they can go ahead and communicate and whatnot. So we have that primary flight display page, which gives us that whole six-pack onto one, and then we have the HSI here, which when we talk about more navigational equipment, this is basically the heading indicator meshed with a VOR instrument, which is really cool. But yeah, so that's going to be the Garmin G5. Just know if we get any sort of faulty reading from the AHRS system or the air data computer, we will get that red X. The G5 will have a backup battery of 4 hours of power. which is really nice, especially if you get a alternator failure or something like that. You know you have 4 hours of all 6 of these instruments on both of these G5s. But yeah, that's going to go ahead and conclude the Pitot-Static system. Went through the airspeed indicator, altimeter, and the VSI. And then the gyroscopic system, we talked about how we actually get that vacuum pressure to spin those gyros, how we can also use the electric system to go ahead and spin that gyro as well, and how this all plays into the air data computer and the AHRS. Some good resources to go ahead and read a little bit more into these. The Pilot Handbook of Aeronautical Knowledge at PHAC is going to be really good tool for you to jump into. If you want to go beyond that, the Instrument Flying Handbook has some really good information on instrumentation as well. And there's just plenty of good YouTube videos out there that go ahead and show you super good visuals. Unfortunately, I'm just working off of Google Slides, so I can't show you the ins and outs of these gyroscopes. So just do your research, jump on there. Like I said, this is something that will come up on a check ride, so make sure you have a really good knowledge in all of these systems. And 2, if any of these were to fail, you know what to do in flight, and you can make a safe decision from there. But yeah, that'll do it. Thank you so much.